In post-war Britain, society was rebuilding itself from the rubble. At the exact same time, it was quietly laying the groundwork for the computing age. Early computers were industrial behemoths. Machines like Colossus relied on floor-to-ceiling banks of vacuum tubes and miles of wiring, requiring intense physical labor to run. The prevailing scientific consensus of the era was rooted in an observation made by mathematician Ada Lovelace a century prior. She noted that machines can process strict orders and crunch numbers, but they lack initiative. They cannot originate anything new. Suggesting a room full of hot metal and glass could possess a mind was considered professional suicide. It was strictly science fiction. Alan Turing, a brilliant mathematician and codebreaker, looked directly at this absolute scientific consensus and rejected it. In a 1950 paper, he posed a simple question to the academic establishment: can machines think? Computing at the time meant human operators feeding rigid punch cards into massive calculating machines. Turing projected a purely psychological concept onto these unthinking mechanical gears. Turing threatened the human monopoly on intelligence. He treated cognition as a process that could exist independently of biological brains. Up to that point, academics debated machine intelligence by trying to perfectly define human consciousness. This trapped the field in an endless loop, ensuring machines would automatically fail any test simply because they weren't biological. Turing sidesteps this philosophical trap entirely. He proposed an interactive social parlor game instead of a strict scientific measurement. This diagram shows his imitation game. An isolated interrogator guesses who is the hidden man and woman via text. Turing then replaces one human with a computer, tasking it to functionally deceive the interrogator into believing it is a person. By setting up the test this way, Turing shifted the benchmark of intelligence. He abandoned measuring internal biological mechanics and focused entirely on external behavioral deception. Turing's thought experiment functions as a mirror. It turns the focus away from the microchip's consciousness and onto our own psychological vulnerability. Turing made a rather solipsistic observation. Solipsism is the philosophical idea that only one's own mind is sure to exist. We cannot truly prove the humans around us are thinking. We observe their behavior and grant them a polite convention that they possess a mind. If an artificial system successfully mimics that social dance and tricks us, our cognitive architecture automatically reacts. We extend that exact same polite convention to the machine. Intelligence ceases to be an exclusive biological property. It becomes a mutual social agreement required for meaningful interaction. By prioritizing behavior over internal mechanics, Turing moved the goalposts of AI. The field began to treat intelligence as a byproduct of social interaction rather than just high-speed calculation. This focus on interaction eventually moved out of the lab and into global networks. Today, software agents handle our requests and manage our data, creating a world where natural and artificial intelligences are constantly intertwined. Turing deliberately left the question of a machine's true internal consciousness open. In practical, daily social interactions, the distinction is often irrelevant. We participate in Turing's parlor game every single day. We extend our trust and polite conventions to digital interfaces without knowing who or what is on the other side. There is a massive, glaring limitation in Turing's model. It relied entirely on text, representing an abstract, disembodied brain floating in a void. Nature built intelligence from the bottom up. Organisms had to master physical survival and movement long before they developed higher reasoning. AI has undergone a reversed evolution. We built abstract thinkers first. Now scientists are giving those cold minds a physical presence to perceive the world. Which leaves an open question. Can true, complete intelligence ever exist solely on a hard drive? Or must a machine first learn what it means to survive in a physical body?